Jen Fuentes, and I will spare y'all from running down the list of my many roles here at CMG and limit it to being one of the IT solution advisors here. I'd like to welcome you all to the crash course on machine learning. During this webinar, you can follow along with the code and data sets using Google Colab. We're going to give you a fire hose version of artificial intelligence, machine learning, and natural language processing in the form of slides, discussions, and demonstrations. But like I said, don't worry, we are recording this, and upon request, we can definitely send you the link once it's posted on our YouTube channel. So the goal of this webinar is to give you some perspective on what AI is and how you can apply it to solve problems. ML and NLP are deployed in more places than you may already know. When you say, "Hey Google," or "Alexa," you're talking to an NLP application that has been trained to respond to you, or in some cases, randomly talks to you, which is why I don't have one. Or what about when Netflix recommends movies or shows you may like based on something you or your kids may have watched, like Puppy Pals on your account? Or when Amazon recommends a product based on recent purchases. This is all developed by using machine learning. Even the chatbots you may interact with, which is, in my opinion, is on way too many websites, but I think you get the point. Now, you'll hear the word model a lot today. While it is not precisely the same thing, you should interpret the word model as an application. Think of NL and NLP this way. It enables you to solve problems that are not easily achieved otherwise. ML and NLP do not apply to every problem. As cool as I think it would be, you can't just sprinkle AI on everything, even though some marketing may lead you to believe differently. AI, or machine learning and natural language processing, work well together. The problem is based on structured or unstructured data. Human level performance can be achieved relatively easily with a properly engineered data set. Most data scientists and ML engineers spend their time on data engineering and pre-processing and less time on model engineering. Today, we're going to give you some background on the terminology, a few use cases with sample code, data sets, and demonstrations. This will give you some ideas on how you could use this terminology to solve problems. I'd also like to quickly mention, we will have a live Q&A session at the end of this webinar, but should y'all have any questions throughout the presentation, please don't hesitate to put it in the chat. Before we go over the agenda, I'd like to quickly introduce my amazing crew that's joining me today. We have Anthony DiDonato, and not only is he the founder of Career Mentor Group and our sister company, Critical Design Associates, but he's also one of our principal architects. Tom Wilson, our Senior VP of Pro Services. Christian Myers, one of our lead engineers. Aman Motazedian, one of our awesome architects. Mateus Goncalves and Adam Rubik, which are two of our amazing DevOps and ML Ops engineers. Without these guys, this event would not be possible. So thank you guys for being such badasses and making this webinar possible. Let's give them a high five, guys. This crash course will focus on a few different use cases and techniques for employing machine learning and natural language processing. As I mentioned before, we will give you some background on these topics, a description of the use case, followed by a demonstration with links so that way you can run the samples on your own. If you want to follow along, you can run a copy of each data set and code set in the form of a Jupyter notebook in Google Colab. The link will be copied into the chat so that way you can get set up while listening to the presentation. The demos and use cases will follow the overview, so you'll have some time to get ready. Before we get too far into the weeds, I'd actually like to hand it over to Anthony so that way he can quickly give y'all a run through of this process of how it works.
Hey, thanks, Jen. All right. Hopefully you can all see my screen. It looks like 32, 33. I'm sure that number is going to keep going up. The link that was copied into the chat is a link to a README. And from there, you can find all the code and data sets. So if you were to click on that link and launch it, if you haven't logged in, it's going to request that you log in. You'll be able to see all the different labs or Jupyter notebooks. All of the data sets are here as well. And in the README, You'll notice each of the links are there as well. If you don't have Google Colab and you haven't set it up before, or you don't have a Google account, you will need to log in and enable the Google Colab application. The steps to do so are in the README. Back to you.
Hey, thanks, Anthony. I'll jump in here. Just to formally introduce myself, my name is Tom Wilson. I oversee professional services here at CMG. Before we get into the demos, I actually want to give you an overview of what machine learning and natural language processing is. We'll set that in the context of artificial learning. Now, bear in mind, this is an introductory crash course. So our goal here is not to get in depth in every area, but we do want to give you some exposure to give you orientation to it. We don't want to be a scary math class about it. So kind of think of this like machine learning and natural language processing as advanced geometry without having to do all the math. So let's jump into artificial intelligence. As you'll see from the diagram, AI or artificial intelligence is a broad field of study that covers the use of technology to develop intelligent machines, and typically intelligent computer programs. It's artificial because it's intelligence demonstrated by machines, in contrast to natural intelligence, that is intelligence displayed by humans or animals. So when you think of AI, there's kind of three broad categories you can think of. One is machine learning, the second is robotics, and the last is natural language processing. Now, some of you will say you'll hear AI, and what does that mean? Well, more or less, you have to ask, what do you mean when you say you're using AI? And so we'll get into that, and hopefully today, the demos, we get a better feeling for that. AI has a lot of applications that it can be applied to. Understanding human speech, competing in strategic games like Go or chess. You may have seen Watson on Jeopardy years ago. Plain and perfect information games like poker. You see it used in self-driving cars and content delivery networks for intelligent routing, and even in military simulations. So the applications, they're quite broad. You've probably heard this in the language that's used out there. So let's talk a little bit about the machine learning definition and try to drill down what it really means. If you look, the way machine learning is defined on Wikipedia is the study, and we would also say the use or application of computer algorithms that improve automatically through experience and by the use of data. Now, I want to use this definition to draw out some important elements of what machine learning really involves. One is you'll see the word data. The second is the use of algorithms, or what you'll hear referred to as models, to analyze that data. The third is experience. For the computers, you'll hear us talk about this a lot. In the models, we train them, so you'll hear training. And then there's a fourth word that we'll get to. So you want to think about data, algorithms, or models. The third is experience or training. And then that fourth word that I want you to think about is really what you're aiming at, and that is the outcome. And many times you'll hear this in the words of prediction or intuition, that the models make a prediction or make an intuition about something. Now, that'll give you something to hang your hat on as we talk through this, but let me give you kind of some basic components of understanding machine learning. So here's a simple way to look at it. One is machine learning has input. Typically, this is large amounts of data. Secondly, machine learning is the machine learning model. And then the third thing, as I mentioned earlier, that's really important, it's ultimately the outcome that you want. What result do you want that model to produce? That's your prediction or intuition. And we can't forget, and this is really essential in machine learning, that that model requires experience or training. So conceptually at a high level, you can see it's fairly simple. Input data, train the machine learning model, get your outcome that you desire. Now, let me give you examples of actual common uses of machine learning, and we're going to demo these later today. One is analyzing data to make a prediction. And notice you're predicting an actual value there on the right. That's called regression. A second one is actually using a machine learning model to group data, and this is called clustering. And then a third way that it gets used is to analyze the data to identify a group that they belong into. So you take the data, you look at it, and you find groups that you may not already recognize. This is called classification. So you'll see input, put it through the model, and then you have an expected outcome, a predicted value, a grouping, or a classified item. So we're going to see these in action in the demos that are to come. Let me talk a little bit now. How does this actually work? What does it look like if you try to put machine learning into production? Well, fundamentally, you start with a use case. What is it you're trying to solve? As Jen said, you can't just sprinkle AI or machine learning on everything. You need to think about what you're trying to solve. It may be a regression problem because you want an actual value. Classification because you want to group things. It may be clustering because you want to put them into unidentified categories. So just clear, classification is to classify those models into a particular group. So once you do that, you gather data. Now, what you need is large amounts of data. And fortunately, in today's era, that's not a problem. Now, that data can be structured or it can be unstructured, but you'll see as we go through the process, ultimately, you'll get into a structured format that can be used by the machine learning model. You need to clean that data. That's probably the biggest part and time consumer when you talk about machine learning. So what you do is you process and you label the data. You're going to clean it up, and you'll see as we talk here in just in a minute in our next slide that some cases you need labeled data to actually execute on the machine learning model. So then you process that data and label it. And as you continue forward, you're going to hear a term called feature engineering. This is where you identify features in the data that are important to making that outcome occur, the prediction or intuition. A simple way to think about this is a feature in feature engineering is some attribute, characteristic, or property of the data that's important to achieve the outcome you're looking for. Simply put, with all the data that you have, you've got to find what's statistically significant because stats matter. As we said, this is effectively a math problem that you're trying to solve. After you do that, you're going to select a model. Now, as you gain experience in machine learning, you know which model. As we noted earlier, different machine learning use cases require different approaches for regression, classification, or clustering. So you got to figure out which model works best. So you're going to select a model, and then you're going to build and train that model. You want it to learn, how do I take all this data, and if it's labeled, using it in the labeled way or unlabeled and to cluster it, you train that model, and you're going to try different models out. And as you'll see going through some of our demos, there's different ways to verify what the best model is. And then finally, and this is where the rubber meets the road, you're going to deploy it into production. Now, this isn't just get a Jupyter notebook, show your friends and family because you did something cool over the weekend. This is actually get into production. And the way you'll hear people talk about that is using machine learning operations or ML ops. That's the pipeline deployment, evaluation, maintenance of the overall machine learning model. Now, let's step forward and talk about the type of training or learning that can occur in a machine learning model. And what you're going to find is it's all about the labels. So there's two basic high-level ones, and a third one I'll reference here at the end. The first is supervised learning. And when you hear that term, supervised learning, you think about labeled data. This is typically used in those cases of regression or classification. I need to put a particular object of the data into a class, or I need to make a prediction of an actual value. Let me just give you a simple example using fruit. So you'll see on your screen, you've got apples, bananas, pineapples, and grapes. Now, what you do in labeling is you would label them as apples, bananas, pineapples, grapes. And so then the machine learning model now can look and say, oh, that's what an apple is, what a banana is, grape, pineapple, you get the idea. Then you run that through the model because it learns from those examples. So that's why you're using labeled data to train the model so it can classify the data. Ultimately, puts it through the model and it goes, oh, I see that, that's a grape, and it classifies it. Now, another way that you can do or use machine learning is through unsupervised learning. You use unlabeled data. What you're doing here typically is clustering. And what clustering does, it's going to put data into groups that you may not have previously thought about or been identified. And let's use our fruit example again. So here you'll see you've got all kinds of fruit laid out. They're not grouped, they're just random data. And what the unlabeled data does is a machine learning model looks at it. It starts to identify characteristics about it. So an apple's red and roundish, a banana's long and yellow, pineapples, golden leaves with leaves sticking out the top, grapes round, purple clusters. You get the idea. So it learns those, and as it learns it over time, it can make decisions about how they relate or how they cluster or group together. And so that's what happens with unlabeled data. So there's a third area that we're not going to get into today. You will hear about, you can read more on, called reinforcement learning. This is a punishment and rewards method in a machine learning model. You might want to read up on that more, but today what you're going to see is supervised and unsupervised learning models that we use. So there's another concept that you need to understand in machine learning, and that is active learning, or what you'll hear called human in the loop, or HLI. And it's self-descriptive when you hear human in the loop. You're putting a human into how you're going to train the model. This is a special case of active learning, and this is how it works. First, you're going to train and deploy your model. You begin with this training and it's put in deployment, And then the next thing you do is you're going to randomly sample the data. As you randomly sample that, there's decisions that the machine learning model has to make. And this has to do with a degree of probability or certainty it's making about the decision. So it looks at that and says, hey, this is what I think this data is. And it makes a decision. And if there's a high degree of probability, it actually labels that data. So it says, hey, this is what I think it is. And it puts it in and it pins the data. Now, if it thinks there's a low amount of certainty or probability, what it'll do with it then is it uses the human. It puts a human in the loop. Sometimes you'll hear this called the oracle. It doesn't absolutely have to be a human. There are other cases where it's not. There's other ways to verify that. But typically a human looks at this and you'll hear them called the oracle. The oracle then labels the data and says, this is what it is. Again, you append that into the data. And then your last step in the human loop is you rinse and repeat. So the basic idea is high degree of probability, low degree of probability. If there's a low degree, have a human take a look at us and tell us what it is. So we're almost there to get to the demos. I know this is a lot to take. I feel like the coach giving you the speech before the basketball game. He's like, I just want to get out and play. So a couple last things for us to cover. Natural language processing. Now, when you think of natural language processing, it's simply, you can think of it this way. It's machine learning applied to human speech. And that can be text, written, or it can be speech, actual human speech. Now, more formally, natural language processing is really identified as a subcategory of linguistics and computer science and artificial intelligence, and how it uses machine learning to apply in that area. The goal is to actually understand or come up with a computer model that is capable of understanding the documents or the speech that is spoken. There's a nuance to this as it looks at them. So ultimately what happens is in natural language processing, you're trying to solve these problems: speech recognition, natural language understanding, even natural language generation. And you're going to see some examples we have later that'll help you kind of make material associations with examples. You're probably very familiar with things like Siri, Google, or Alexa. Even this morning, that's how I listen to my news in the morning. I say, hey, Alexa, and that's natural language processing. Last thing, and then we're going to get into the demos and launch into those. We wanted to give you some orientation to common machine learning and natural language processing tools. So we just threw some examples that you'll see here. You can see the labels there on the screen here. What you need to take from here is a couple of things. One is there is a wide breadth of tools. Some of them are free, some of them are not free. And as you get into machine learning, there's a lot of free tools out there to really help you learn them. The free ones you'll see here on the screen, two to really make note of, is the programming languages that primarily get used in machine learning, natural language processing, and that is Python and R. The last thing I want to show you here is pandas. So pandas is a module inside of, or library inside of Python, and it produces what are called data frames. And for those of you that know R also has data frames as a programming language. When you think of it, just think of it, you'll see your example here on the screen, is like a spreadsheet or a database table in memory. That'll help you as you hear data frames mentioned. Oh, what's a data frame? It's like a table or a spreadsheet in memory that's used to actually do the analysis. So with that, we're almost there. Let me get to the demos. Before each demo, what I'm going to do is I'm going to give you a basic overview of the model or algorithm or the technique that's going to be used. And then we'll hopefully give you a better grasp from that of what the demo is doing. So let's start with classification. That will be our first demo. Before we get there, let me just, again, brief overview of classification and give us the orientation again. As we saw earlier, remember, classification is about predicting a category or class, something that's supposed to go into, right? You know the groupings or classifications you want, identify what the object or the data should go into. The key point is that you know what the categories are. You already know what categories you want things to go into. And you'll see examples of things that are called binary and multi-class classification. Using our diagram here on the screen, a binary would be, are these fruit or are these vegetables? Or the multi-class example that we used earlier is this an apple, a pineapple, a banana, or a grape? They're kind of self-descriptive. One or other class, or is there multiple classes to put it into? So here's some examples of classification. The examples, you can see tumors. One you probably see all the time is it spam email or not, speech recognition, etc. So you go through and you can classify different things based off the characteristics or features that the data has. So with that, looking back on all that information, hopefully to give you some things to grasp a hold of. Now we're going to dive in earnest in the demos, and I'm going to hand it over to Christian to show us our first demo in classification and how to identify web pages that are used for phishing.
Thanks, Tom. Before we get into explaining some of the models, let's start off with a use case. A good use case for classification is determining if a website is a phishing site. Imagine we have a person named Bob, and Bob works in the security department. At his company, many of the users fall into phishing attacks from URLs and emails. I'm sure everyone here has seen an email claiming they have won a large sum of money. They just need to sign into Facebook or another site to claim it. To combat this, Bob has devised a plan by using attributes of the web page to see if the site is phishing. Attributes such as URL length. The longer the URL, the more suspicious it is. The age of the domain. If the domain has only been up a day, that's probably a phishing site. And having an IP address in the URL. Sites like Google do not have any IP addresses in their URL. You can see how some of these attributes could cause suspicion. With the attributes gathered for each one of the websites, we compile a data set. You can see each feature or column of the data set is one of three values, -1, 0, or 1, meaning it's legitimate, suspicious, or it's definitely a phishing website. A classification model such as random forest is great for this type of application. Random forest is made up of a ton of decision trees. Let's go through a quick example. But before that, let's go through the data set on our screen. At the top, we can see the first pop-up window, request URL, and URL anchor all -1, meaning they are legitimate. We can also see that web traffic, URL length, and age of the domain are leaning towards the phishing site. And then finally, we have an IP address in one of the redirects, or maybe two of them. So we have a 0 for it being a little bit suspicious. The combination will ultimately make this example a suspicious website. So let's go through a tree. Starting at the leftmost side, our tree will start with a pop-up window. This particular site does not have one, so it gets a -1 value. Next, we go down the tree a level and see if the URL request is too long. It seems the URL is concise, so it is marked as legitimate as well. We continue down this tree until we get to the final result of the site being suspicious. Obviously, the tree would expand much larger than our example, but this is how the decision tree classifier works. The decision tree has a set point to start from and arrives to its final answer after going down the branches. Let's look at another example. For this tree, we're going to start with the same data set, but let's start on the second feature. The URL request is rather short, so the site seems legitimate. Next level down, we see the URL anchor does not change when browsing from page to page, so that is also legitimate. As we traverse down the tree, we ultimately come to the conclusion that the site is suspicious. So we have two trees that go two separate ways to come to the same conclusion. How random forests can be more effective is it takes the output of each of the two trees in our example and formulates an output accordingly. This means each tree has a vote on the final outcome rather than one tree deciding everything. The number of trees in the forest can affect the outcome as well. So now let's jump into the demo. As mentioned previously, if you would like to follow along, please use the links in the chat to access the shared Google Drive where all needed materials can be found. So I'm in the Google Drive right here, and I just want to review. We will need a data set and we will need the Jupyter Notebook as well. So in the data sets folder, we will need the classification websites data set, and you can download it here by clicking on the ellipse. Once you have that downloaded, we'll need to open up the Jupyter Notebook, which is in the classification folder, and it's going to be this right here. While this is opening, we'll just give this a second here. All right, so this is our Jupyter Notebook, and a little bit of housekeeping before we jump into the demo. This is a read-only notebook right now. If you are interested in getting your own copy and having something you can edit, you can do File and Save a Copy in Drive, and that will allow you to edit the copy. All right, first things first, we need to upload our data set. So on the left side here, we can see this folder. If I click on this, you should be able to upload our data set. So I have it right here, and we now have it uploaded. Let's go ahead and run everything, and I can explain as we go down. So the first part, as Tom mentioned, we need to import our libraries. We have NumPy, matplotlib for plotting, and then pandas to pick up the data frame. Next, we're going to go ahead and load in our data set, and we are going to load it into two separate variables. The X variable is going to be our independent variable, and that is going to include everything from the pop-up window column to the having IP address column. We also have a Y variable, which is our dependent variable, and that's ultimately going to be the result of each one of these. Now that we have it imported, we need to take a look at our data set. First, I like to start to see if there's any null values, see if there's anything that I need to engineer to make it a complete data set. We can see here there are 2,901 in each one of the columns, so this looks like there are no null values. Next, I like to see whether the data set is balanced, so I do a value count to figure out how many of each one of the values we have. We can see here we have 1,404 legitimate, 1,096 that are phishing, and 401 that are suspicious. That's going to cause an issue ultimately at the end, because we're going to train more on it being legitimate or phishing and less on it being suspicious. So, we need to equal out this data set. We can see here in the visual as well, legitimate sites severely outweigh the suspicious sites. Before we get into balancing the data set, I also like to take a look at the features and see if there's any indicators of a phishing website or not. Something like web traffic, you can see these are equally distributed, so that's not really a good indicator. But something like age of domain, if it's an older domain, it's going to be a legitimate site. If it is a new domain, it's most likely going to be a phishing site. Or something like having an IP address. So if it has an IP address in one of its URLs, it's either going to be suspicious or phishing. It's never going to be legitimate. So let's get into balancing the data set. I'm going to be using a technique called SMOTE, or synthetic minority oversampling technique. And essentially what this does is it finds its 5 nearest neighbors to an undersampled portion. So in our example would be suspicious. It's going to find its 5 nearest neighbors and create another data point out of that. So we can see previous, as I mentioned, we had 401. After going through SMOTE, we have 1,404 of each one of the values. So let's get into splitting the data set now. We're going to split it into a training set, which we're going to train our model against. And then we're going to split it also into a test set, which we test the accuracy of our model after. The test set is a little bit smaller. It's about 20%. So we're getting a lot of training and a little bit of testing. I know we've already discussed that this is going to be random forest, but I left this section in here just kind of as an interesting point. This is how we do our model selection. I have a pipeline here that is going to evaluate 3 different types of classifiers. We have random forest, K nearest neighbors, and decision tree. And essentially what this does is going to create all the models and create a confusion matrix after to see which one's the best. Down here on our plot, we can see that random forest is 85, 86%. Decision tree is 85, 84%. And then K nearest neighbors is around 80%. So this is how we chose our model for random forest. Now that we have decided, we're going to go ahead and fit our random forest classifier and then predict what the outcomes are on the X training set. Going through this, we can see our model has about an 85% accuracy when we guess what the Y value was going to be versus what it actually was on the training set. And then we have about an 85% when we go through the test set as well. So you can see here that with data that was trained on, or new data, it's going to be roughly the same. So that is good when we're going to roll this out into production. We know with certainty we have 85% on whatever we throw at it. Just to visualize this a little bit and figure out where we might be getting some issues, I've graphed the outcomes. So we can see the legitimate and phishing websites skew a little bit towards suspicious. So this is an overly cautious model. If we added a human in the loop, we could correct some of these and get this more accurate. Just as a reminder, we started with 1,404 legitimate, suspicious, and fishy websites. So that is my demo. And with that, I'll hand it back to Tom.
Hey, thanks, Christian. Great demo of classification. Let's move on to regression. Let's go back and just remember the basic concept of regression is. At a basic level, regression in machine learning is all about predicting real values. You want to identify a pattern in the data that predicts an actual real value. A simple example is simple linear regression. You're just doing a straight line estimation or pattern match against the dots that you see here on the screen. Some of you may remember this from high school, for example. I learned it as y equals mx plus b. Here you see it as y equals bx plus a. Simple linear regression. The key point here is that when you're using regression algorithms or models in machine learning, that what you want to do is predict a value, right? That's the prediction that we talked about. As Christian mentioned, even in his demo, that value is the dependent or target value. The other values that you see that are used to make that prediction are known as the independent variables or predictors. In regression, you can have a lot of different ways that it's used. Here's just 4 ones that you may have heard of. Predicting a salary range. So you can look to say, hey, what's salary look like in the future based off historical data? Forecasting future price index on commodities or stock based on certain attributes or features that it's had. Temperature prediction, predicting congestion patterns inside the city when you're looking at how cars navigate and making those predictions. A lot of different use cases, and you'll see here, I'm going to hand it off to Aman to give us our demo of regression so we can see how it works.
Thanks, Tom. Hi, everybody. What I put together today for you is a demo where what we'll be doing is analyzing some ServiceNow help desk tickets and logs, and we'll be predicting the time of completion for this tasks based on some of the initial ticket settings. This can be useful if you're trying to adjust expectations or set SLAs. Before we get into that, though, I wanted to review some of the techniques we'll be using to analyze the data. So the first one is feature scaling. What I have here is just kind of a very basic representation. We've got these red dots and these blue dots. Notice that the red dots have a much higher numerical value than the blue dots. And so if we were to train a model on this, the model would skew heavily towards the red dots. So what can we do to fix this? We can use feature scaling. And what feature scaling does is it remaps the variables onto a smaller number line. So the red dots representing one variable have a same relationship between each other. And similarly, the blue dots will have the same relationship between each other. However, between the red and the blue dots, it's much more equitable. So when we create a model off of this, the model will be much more representative of all the data. So just to kind of summarize, we're basically taking a larger number line and compressing it down to a smaller number line. So that way, in the end, we're comparing apples to apples. Another important concept is support vector regression. Now, this is what we'll be using to create our model. And it has some very beautiful, elegant mathematics to determine the outer boundaries of your data. But that's not something that we actually have to do here. We're just going to use the tools, and the tools will do all this for us in the background. But once those outer boundaries are computed, the model is the line that is in between those outer boundaries. Another important concept are the kernels within support vector. So when you're computing your model within support vector, you can use different kernels. And from a high level, kernels are a way of remapping your data points to a higher dimension, and this increases the flexibility of your model. So the most basic kernel would be the linear kernel, and this is very similar to linear regression that Tom mentioned. It's not the same. You're not going to get the same results all the time, but it's very similar to linear regression. Similarly, we'll be looking at the polynomial kernel, which again is very similar to polynomial regression, but it's not the same. These are based on those outer boundaries we were discussing. And then finally, we'll be looking at a radial basis function kernel. This is the most flexible. It's very widely used and will give us a very accurate model. And finally, we'll be talking about R squared for validation. So one thing you'll be hearing again and again is you'll be hearing about how we're separating our data into training data and test data. We use the training data to create our model, and then afterwards we want to do some validation, and we need a nice solid way of evaluating that. So what we'll do is we'll take our test data, which has been separated, and we'll use it to predict values with our model, and then we'll compare that test data to our predictions. And R-squared is a way of doing that, and it creates a score. And so 90-95 is a good score. Much lower, and you have low accuracy, you need to work on that, and much higher, and you may have overtrained your model. These are some of the other methods used to evaluate accuracy, but we're just going to be focusing on R-squared today. So I'm going to jump right into the demo. So this is the same notebook. This is the notebook for regression. It's loaded up. You can load the data set here, just like how Christian showed you. I'm not going to go over that, but Christian already showed it. So libraries we'll be using, pretty basic, NumPy, Matplotlib, and Pandas. And here we're loading the data set, and we're going to take a look at the data. And one thing we'll be doing is we'll be dropping a couple of columns which are full of text data that we're not going to be analyzing. Regression doesn't really work with text data very well. So once we do that, we're going to take a look at our data, and we're going to be doing some of the same balancing techniques. But again, I'm not going to go too in depth into that. We're just basically trying to keep a certain range of the data in place so that we're not overrepresenting certain data points. Finally, here we're going to be looking at feature scaling, like I mentioned before. So this is just one of the variables, and we see that the range here is from 4,000 to 10,000 for the dependent variable, and then 1 to 7 for the independent variable. And after feature scaling, all you're doing is plugging the values into this function. And here plotting it, you see that everything's now been compressed into a smaller number line. So you've got -1 to 3 and -6 to 4. And this is going to be applied to all of the independent variables, not just category. And so that way, when we do our training, it's going to be more representative. Now here we're splitting our data to training and test. And then here is where we train the model. Pretty straightforward, nothing too complicated. The key point here is we're using support vector regression for everything. And in these lines, we're defining which the kernel is. RBF is actually, which is radial basis function, is actually the default. So if you don't define it, you're going to use radial basis function. But I left it here explicitly just so you can see. And then this is the training. Doesn't take very long. When running the cell itself takes a while, but actually getting the training done isn't super difficult. Here's where we're going to do some evaluation with R-squared. So what we end up doing is we take that separated out X test data and we run it through our models, and then we compare it to the Y test, which is the actual values. So we see here that linear is 93.9, polynomial is 82.0, and RBF is 94.3. So linear and RBF are pretty good, and polynomial needs a little bit of work. Here I separated out just a single row of variables, and what I want to do is just look at a specific outcome. So the actual value was 7,878 seconds. For linear, it predicted 7,372. For polynomial, 7,205, and for RBF, 7,338. So not bad. Me having worked in IT for a long time, I would go ahead and triple that number before setting expectations. Here's one thing that I think is very useful with regression, which is determining the feature importance. I think Tom mentioned something about this a minute ago. And what that means is we're using all these different variables to calculate our time to resolution, but which one is the most important one? Which one has the most effect on that outcome? And from here, we're seeing that subcategory 1, that value is what's having the most effect on the outcome. And finally, we're just going to do a little visualization so you can see what the models look like. And in order to do that, we create some filler data and run it through our models and then plot. So we have the linear here is the blue line. The RBF is this slightly curvy green line, and the polynomial is this much curvier orange line. So we can see this probably has a good visual of why our R-squared scores for RBF and linear, we're much closer, much more accurate, while polynomial has this larger distance at the ends, and that's going to affect its R-square score. So with that, that's all I've got for the demo. Back to you, Tom.
Hey, thanks, Aman. Great demo. Appreciate the overview of regression. So we've seen a demo of classification. We've seen a demo of regression. Let's move to our third demo now of what clustering is. Recall, as we talked earlier, clustering is about identifying groups or clusters of what's in the data. And what's key to remember here is you don't know what the groupings are. You're really looking for groupings that the machine learning model could identify for you. This makes the clustering exercise of the machine learning model an unsupervised learning model. It's not depending on that labeled data. It gets unlabeled data and it's going to try to find how they cluster together. To think of clustering, what you really need to think about is they are mathematically close. You have to calculate distance, and you're going to see in the demo what that distance calculation looks like and how you get this into a math exercise to identify your clusters. Some examples of clustering and the way it gets used. One is in marketing customer segments. You get all this marketing data, you figure out how do these marketing segments fit together? How do these people fit in various groups or clusters? You probably have seen this in some of your shopping exercise when it said, hey, we found other people that when they bought this, you seem to fall in that group that also might be interested in these other things. You could use it in biology for identifying species, and that would be an exercise like you found a new species that never existed before. Libraries for types of books to see how ones that maybe aren't classified that way, how they associate, and you find a new grouping. Insurance fraud is another area where you can look at in fraud data and figure out how it clusters together to now you identified fraud instances. City planning and housing and how it lays out, weather, natural disaster, what are your at-risk and dangerous areas for a hurricane and flooding, et cetera. So just keeping those in mind as you're going to take this unlabeled data and find out how it associates together into clusters. Let me hand it off now to Adam to give us an overview of clustering.
Thanks so much, Tom. Let's talk about the use case. So over the past few years or some period of time, help desk tickets have piled up. These tickets are for all sorts of different things, from login issues to device hardware settings, and the tickets are completely unsorted. Management would like us to be able to sort them into distinct categories so we can know what types of tickets are most common, and this will also help future tickets get resolved faster. We could do this manually by assigning a couple people to go through the tickets one by one and sort them. However, there are a few clear downsides to this method. We do not know how many categories there are, so the first thing they would have to do would be to figure out all the different categories, and then they would have to go back and sort every one of the tickets. This would be an incredible waste of time, and it would be highly inefficient. Instead, we could use a clustering algorithm. The clustering algorithm will perform this task much quicker than a human, and will build in some human-in-the-loop validation to check that the clustering algorithm is working correctly. This approach is quicker, and it's a more efficient use of the employee's time. So to summarize, we're going to use clustering to figure out how many categories there are in our data, organize the tickets into the different categories, label the categories, and validate that the tickets were sorted correctly. Let's talk about some of the techniques we'll use to accomplish this. The first thing we need to understand is converting text to vectors, taking sentences and converting them into a number. We do this because the clustering algorithm needs a number representation of the help desk tickets. We can't simply just feed in the word data itself. So we'll start with these two sentences. I hate it when it gets cold outside, and I love sleeping in on the weekend. To form a vector, we first need a vocabulary, or a mapping of words to numbers. So we split all the words up and assign them each a number. You can see that here in the middle of the screen. So cold gets mapped to 0, gets mapped to 1, hate to 2, I to 3, and so on for every word that is used in those two sentences. Then we piece everything back together with the words represented by their associated number. The first number here represents what document that word is associated with. So it's either a 0 or a 1 because we only have two sentences here. The second number is the number used to identify the word. So in this first one, we can see the number is 3. If we go back to the vocabulary and match that up with the word that's associated with that number, we'll see that I corresponds to 3. So we know that first word is I. And then the last number we see on the right is how many times that word appears in the document. Most of these are 1, but there is one word that shows up twice. So again, we can see the number for that word is 5. We can go over to the vocabulary, look, and see that the word that is associated with 5 is it. And we see that this one shows up twice, which makes sense because if we look at our first sentence, we see it shows up twice. So that's just a quick intro on count vectorizers. We'll use this data as input to our next step. Our next step is term frequency inverse document frequency. So what is TF-IDF? It's a statistic meant to show how important a word is to a document in a series of documents. The higher the score, the more important that word is. And it's also important to note that every word has a TF-IDF score. This score is used to gather more relevant results in search engines, and generally it's a good metric to understand the characteristics of a document. So it's perfect for this application. To understand more about how these scores are calculated, let's take a look at a couple of formulas. So just load them all up. Okay, well, maybe not. You could spend an entire afternoon looking at formulas trying to understand TF-IDF. Knowing the different formulas is important and it's something you can explore on your own, but for this webinar, it's not really necessary to know them. So let's take a look at a simplified version. To begin, we'll start with the count vectorizer, which we saw in our previous graphic. Now we'll go through the count vectorizer entry by entry and calculate two things, the term frequency and the inverse document frequency. We'll end up multiplying these two scores together, so an important word will have both a high TF and a high IDF score. Calculating term frequency is pretty easy. For each word, we find out how many times it appears and divide that by the total number of words in that entry. The TF score gives us some insight as to how important a word is to a single entry. Then we'll calculate the inverse document frequency. The IDF score essentially shows how common a word is throughout all the entries. The more entries a word appears in, the lower the IDF score. And on the flip side, the fewer entries a word appears in, the higher the IDF score. So a word that is only in a few entries would be really important to those entries and thus have a high IDF score. Once we finish those two calculations, we can calculate the TF-IDF statistic. And we'll do this for every word in an entry in all of the entries. Here are the example TF-IDF scores for the sentence, "I hate it when it gets cold outside." So you can see that here on your screen. What we've essentially done is broken down the sentence into its digital fingerprint. And now we're really ready to start doing some of the machine learning. The first thing we have to figure out is how many clusters exist in our data, or answer the all-important question, how many categories are there? To figure this out, we can use something called the elbow method. We simply feed in our data, display a graph, and look for the elbow point, or point where the graph begins to flatten out. So for this graph, we can see the elbow point would be at 5 clusters. Therefore, we have 5 clusters in our data. Now we're ready to start clustering the data, and the form of clustering we'll be using is called k-means clustering. This algorithm is unsupervised, so that means that we don't need to have pre-labeled data, which is perfect for our example. Based on the number of clusters we input into the algorithm, it will go through our data and organize it into that many clusters. We'll dive into this more in the live demo coming up shortly. Once we finish running our data through the algorithm, the next step is human-in-the-loop validation. Essentially, we want to check the algorithm's work for any mistakes. This process can be as hands-on or off as we'd like it to be. We could validate no samples, we could validate a random sample of the data, or we could go through and check every single data point. It's really up to you and the data that you're working with. But once we finish validating our data, we're done. Okay, now let's dive into a live demo and see how these things work with some real data. So I'll just load up the Google Colab. Again, these are publicly available, so if you want to follow along, feel free to do so. I've also already imported our data, so we're ready to go there. And at the top, I've listed out several articles that I used to build the demo. These articles have a lot of code in them, and they have a lot more explanations. So it's worth going and looking at before you really dive into it. But for sake of time, we're going to skip that. So the first thing we do is import all of our different libraries, and then we'll load our data set. And here we can see as our data set, again, it's unlabeled, so there's not really any categories on these tickets. We just have our ticket description. And if we look, we see things like user needs updating. Looks like this user forgot their login information. We have some issues with Windows logging in and a couple of Kronos password issues. But all in all, we have about 800 tickets in total. So like we saw in the PowerPoint, the first thing we have to do is vectorize our data, and we'll use a count vectorizer to do this. Once we've actually vectorized our data, we can take a look at the vocabulary, which is something we saw in the PowerPoint. This one's a little bit bigger, but it's pretty much the same. So we can see access is mapped to the number 3, account to 4, admin to 8, application to 16, and so on for basically every word that appears in our help desk ticket data. In total, our vocabulary is about 280 words long. The next step is to calculate the TF-IDF scores, and we'll do this using a TF-IDF transformer. So we can run that, and then we'll print out a sample ticket. And we can see our sample ticket is 80 password reset. And if you look at the TF-IDF scores, we can see 80 as the highest score, then reset, then password. And for every other word that didn't appear in the ticket, they're just given the default score of 0. So let's stop for a second and just think about what we've done already. So we've loaded in our data, we've vectorized it, and now we've calculated the TF-IDF scores. This is where the bulk of the issues come up. And this is where we spend a lot of our time, is actually pre-processing the data. Now that we've done that, we're ready to start doing some of the ML stuff. So we'll start with the elbow method. So I'll go ahead and run this cell, and we'll see the graph similar to what we saw in the PowerPoint, but it's a little bit different. The elbow point isn't as obvious, but we can still see one right at about 7 clusters. So we know we have 7 different categories within our help desk ticket data. And once we've calculated this, we can now actually train our k-means model in the next cell. So we'll input the number of clusters that we have, which we just saw is 7. We'll actually run the model, and then I'll make a new data frame. And within this data frame, we'll actually see our ticket description, the TF-IDF score, and the cluster. So if we look at this one, Windows login, we can see the scores, and this is in cluster 3. Same thing down here, we can see our Kernels password ticket, and this is in cluster 5. So quickly, let's just step back and actually look at what some of these clusters look like. So I'll print out a word cloud for each cluster, and that'll kind of give us some idea as to what tickets are associated with them. So if I scroll up, this first one looks pretty good. Ideally, we don't want to see a lot of words in the cluster. The fewer the words, kind of the more tightly packed that cluster is. So we can see here's a pretty good one. Most of these are actually looking pretty good so far. Now here we do see one that is a little messed up, which is kind of to be expected. We're not going to expect our algorithm to work perfectly every time. So we'll go back later and be able to fix this. But if we continue, we can see most of these actually look pretty good. One problem we can see, however, though, is that currently the clusters are just given a number. So if we were to pass this on to someone who's, say, going to solve some of these ticket issues, if we just say, oh, that's in cluster 3, that doesn't really help them so much unless they actually help train the model. So you want to give these clusters names. So when we're passing someone a ticket, we can say this is going to be a Chronos ticket. It'll make it much easier for them to resolve the ticket. So what we're going to do is we're actually going to name the clusters. So we'll add a new column called cluster name. And then I have a for loop that's going to go through each cluster and display the top 7 words. Most of the time, this will be enough to kind of name the cluster, but sometimes it's not. So we'll be able to get more information if we need to. But for this first one, we can see this is obviously our CRM cluster. So we'll just name it that. The next one, the most common word is AS400. So for this cluster, we'll just name this one mid-range. The next one, our third cluster, is also pretty easy. We can see, we'll just name it SAP. And here we get to our fourth cluster. This one's not super obvious as to what's going on. So if I hit the plus sign, we'll remember that this is the cluster that has a lot of information going on. So we see things here like login issues, on-demand, password reset, Chronos CRM application. And if we look, we've also printed out a few random tickets in here, and these are kind of all over the place too. So this is kind of like our catch-all cluster where tickets go if they weren't able to really find anywhere. So we'll just call this one generic. The next one, we can see it looks like on-demand is kind of the main theme. So we'll just call this one on-demand. The sixth cluster also is pretty straightforward. We'll call that Chronos. And then finally, we have our last one, which is not super clear exactly what's going on. So we'll go ahead and hit the plus sign again. Here we can see things like password reset, reset, unlock. We need a lot of passwords reset in our random tickets. So we'll go ahead and call this the domain cluster. Now, if we print out our data frame again, we can see we actually have our cluster names there. So if we're passing in a Chronos ticket, we'll be able to just say, this is a Chronos ticket before we actually pass it in. We won't have to call it by its number anymore. The one other problem that you can see here, though, is that if we look at the ticket right below, if we actually read the description, we see it's user is unable to reset password for Chronos. However, this has been put in the generic cluster. Obviously, this is a Chronos ticket. This is where we use human in the loop validation. Now for this demo, I'm only going to go through 5 examples, but you can change this and increase it as you want later on. But basically, we're going to go through, and the first thing we're going to do is we're going to print out the ticket description. We're going to print out what cluster the ticket was classified as. And then if this is correct, we'll just type yes. If not, we'll just rename it to whatever cluster it should be in. So for this first one, we see CRM application password locked out. It was classified as CRM. So that looks pretty good. So we'll say yes. Here we see email password doesn't work after running from leave. This was classified as generic. That looks good. Here we see SAP PS5 login. It was classified as SAP. That also looks good. We see AS400 login was classified as mid-range. We'll go ahead and mark that one as correct. And then finally, we see the same thing. So we'll go ahead and mark that one as correct as well. I'll try running this one more time to see if we actually get one that we need to reset. So I'll go a little bit quicker this time, hoping we get one. Here we go. So we have AS400 account enabled. And this ticket was actually classified as generic, but clearly as we've seen, this should actually be a mid-range ticket. So we'll go ahead and just correct that one. And the other two look pretty good, so that's fine. So again, you can mess around with this more later, but because we're a little time sensitive, that's where we're going to stop for the human loop validation. So the final thing to do is to actually look at our results. So if you remember, we started off with an unlabeled data set that was just the ticket description, but using clustering, we were able to actually define the clusters for the tickets and then group them and organize them in that. So that's it for my demo. I'll pass it back to Tom, and thank you so much.
Hey, thanks, Adam. Really appreciate that demo of clustering using K-means clustering. So let's jump to our next demo, which is going to be in natural language processing. So you may remember, we went over this earlier, that natural language processing is
Sorry,
up.
Tom.
Yep, no worries.
Sorry. You said we're jumping into the demo, so I pulled it up.
Okay, we're going to jump, not quite that fast. I'm going to share back the screen here. You guys, there we go. So on the natural language processing, just real quick as an overview here, just a reminder, natural language processing is all about machine learning applied to human language, that is to speech and text. You probably use this every day with the Hey Siri, the Hey Alexa, Hey Google. And apologies if I just set all your devices off because now they want to answer a question. But that's all about speech recognition, natural language understanding, and ultimately natural language generation. You'll see a lot of different applications of this. So some examples, one is I guess in Jen's case, the infamous chatbots on all the websites you go to and how they pop up and ask you and can give you guided advice when you're asking a question of them. Sentiment analysis, when you look at tweets, text, and reviews, reviewing resumes is another example of what you can do for natural language processing of documents that are written. You'll see this in Customer Service Center where they can do call analysis, ticket analysis, which we've actually done here at CMG, and looking at service desk tickets and patterns and how to ultimately use NLP even along within classification. Email response generation. You get emails in, you want to auto respond in a certain way, but you want to have the same nuance, the same tone that maybe you typically use in your writing. That would be another way that you could use it. So there's a lot of different use cases. So now I'm ready for you, Mateus. Now I'm going to hand it over to Mateus to give us an overview and a demo of NLP using what's called linear support vector classification.
Thanks, Tom. Let's jump into the use case. So we'll be examining a situation where help desk tickets come in via email, and we want to automatically determine what class those tickets belong in based on the description provided by the user. We have some data to work with that's comprised of ticket descriptions and their respective classes. We'll use some of this data to train a model, then use that model to predict classes for novel ticket descriptions. Then we'll analyze the model's effectiveness, look at the incorrect predictions, and see if we can understand why certain issues may be occurring. We'll be using a few techniques to help us with our task. These are term frequency inverse document frequency vectorization, linear support vector classification, term frequency distribution, word clouds, and n-grams. Don't worry if you're not familiar with all of these. I'll be covering what you need to know for the demo. Term frequency is a representation of the counts of each unique word in a sample of text. For example, in these two sentences here, most words appear once, but how, are, and you each appear twice. We would say that these terms are twice as frequent as the others. And then n-grams. Simply put, n-grams are chunks of n terms from the sample of data. For example, if our text is, wow, this text is so interesting, then these are what you would see for the 2, 3, and 4 grams. But as you can see, there's no mixing and matching of the order of terms. They are taken in contiguous chunks. And with that, I'll go on into the demo. I'm using the NLP notebook here, and I'm using the clean HD ticket CMG CSV. All of these are available in the shared drives. I'll need to import a few things to get going, but first I'll have to update ML extend. And if you're following along in the collab, you will likely need to as well. And then I'll comment that out and restart my runtime. And I'll go ahead and run all my cells while I'm at it. Yes. Give it a second to run, and all my cells are running now. So we've got our imports here: NumPy, pandas, matplotlib, as we've seen. And then I import my test train split function from scikit-learn, which you'll see later. The first thing we want to do is load in our data. I'll also drop any rows that have junk values so that they don't get in our way. And then this is what our data looks like. We have two columns. One is for ticket description and one is for class. So our data here is labeled. And we can see that we have over 3,000 entries, and there are no null values in any of our rows here. And here's a distribution that we have for classes. Of those 3,200 or so tickets, over half of them are in the domain class. And then, as you can see, half of our classes barely have any tickets at all. And when we plot these values, we can see very clearly that the data is unbalanced. We'll want to fix this before we start using this data. Now, before I start balancing the data, I'm going to do a bit of text preprocessing. I'll import regular expressions to help us with that. And to get into it, I will make a copy of our original data frame, and I'll use that for our ticket description cleanup. For cleaning up the data, I'm going to remove anything that isn't a letter, a number, or a space character so that we end up with clear, meaningful tokens. And here's where I'm using that regex inside of a Lambda function to accomplish that, if you want to dive in. And with all that out of the way, it's time to start removing some tickets from our data. For starters, I don't want to use any classes that have less than 100 tickets, so I'll filter those out, and that'll leave us with these 7 classes: domain, midrange, CRM, generic, on-demand, SAP, and Kernels. So we've cut the number of classes in half, but as we see here, it's still unbalanced. Now, to help balance this data, I'll create a list of the remaining classes, and I'll identify the minimum number of tickets that we have in each class. So here's our list of classes, and we know that we have 110 tickets that are in each of these classes. Now we have enough info to create our balanced data set. The balanced data set is going to need to contain an equal number of tickets from each class so that it's balanced. So I'll take a sample of 110 tickets from each of those classes. And what we end up with is a data set that looks like this. And if we plot those values, we can see that it's balanced now. And now that we have the balanced data, we can start looking at our model. We need to get our data ready to pass to the model so that we can train and then test. First thing we'll do is split this data into testing and training sets. X is going to be our ticket descriptions, and Y is going to be our classes. We'll split X and Y into our training and testing sets. The test set is going to be 30% of the balanced tickets, and then the training set is going to be that other 70%. And as we can see from the shape of our data here, our training set consists of 539 ticket descriptions and classes, and then our test set has 231 of each of those. Now we can work on the model. We need to import linear SVC pipeline and TF-IDF vectorizer to build our model, as well as a couple other things for displaying the results. The text classifier that we're defining is going to pass our ticket description strings through the TF-IDF vectorizer and then onto the linear SVC algorithm. Then we'll fit or train the classifier with the training data. Note that in this step, we are passing the descriptions and the classes to our model. Once that's done, the testing data gets passed to the classifier for prediction. And in this step, we're only passing in the ticket descriptions. We're not passing in the classes. These are the predictions that we get back. I can't really tell you a whole lot from looking at this, so I'll take these predictions along with the Y-test data, which are the true classes, to my results analysis function, which I define here. And it looks like our accuracy is about 96, 97%, which is very high. And our biggest problem seems to be right over here. So it looks like there's some confusion between domain and generic. Let's do a few more predictions and see if this pattern holds up though. And as a reminder, this is how many tickets of each class that we have in the unbalanced data set. So most of them are domain, and then we have 2 or 3, 400 of the others. I'm going to run all of these tickets through our model and see how well it can predict the classes. I'm going to store those predictions in a new column on our data frame called prediction, which we have here. For the first and last 5 that we have, it looks like they're all right. And then I'll make a new column that tells us whether our prediction was right or wrong. If the prediction was right, it'll be true. If it's wrong, then it'll be false. And like I said, these ones are true. And just to get a general idea of how many of them were right or wrong, I've also printed out the value counts here. So in our entire unbalanced data set, we have 2,730 that were predicted correctly and 181 that were predicted incorrectly. And a closer look reveals that we do indeed still have a problem in the same general area. There's a couple mispredictions out here, but the main problem is right with between domain and generic. So I've defined a function here to print out the true and predicted classes together for comparison. And then here's the chart for that. A quick glance will tell us that we are under predicting for domain and that we are over predicting for generic. Now I want to take a look at the wrong answers. And as you can see, the number one problem that we have is that when the class is supposed to be domain, our model is predicting is generic. And the number two problem we have is that when our class is generic, our model is incorrectly predicting that the class is domain. Let's see if we can find out why this is happening by using some additional natural language processing. I'll just need to import a couple things here: word cloud, word tokenizer, and frequency distribution functions to make everyone's lives a little bit easier. And I'll define a function to display some graphics for frequency distribution, a couple functions. I'm going to take all of the text from our unbalanced ticket descriptions, and I'll display that in a bar chart of the most frequent words, as well as a word cloud. Right off the bat, the most common words are password, reset, and login. Then we have some words that are not particularly indicative of any specific class. And while this is useful, I suspect that it may be skewed since the data was unbalanced and there's a disproportionate amount of the domain tickets. So here are the same charts, but using the balanced data. So this is generated from the 770 tickets that we had split evenly between the classes. We can see the same pattern of password, reset, and login, but then we get some words that are more specific to the individual classes, kind of like Kernels, SAP, on demand, and so on. This tells us that password, reset, and login are common among all the classes, not just domain, like we suspected it might have been. And with that, I'll take a look at the text from each individual class and see if we can differentiate between them that way. And make this a little bigger. And here it's becoming more clear. For 5 of our classes, their most common word is specific to that class. So for mid-range, we have AS400, Kernels is Kernels, SAP, and that pattern continues. But like we saw with Adam's examples, generic starts off strongly with login, password, and reset, those kinds of words. And if we look at domain, those are the words that are also the most frequent. But the fact that those words are ranked so highly across the board means that they're going to get weighted lower due to that TF-IDF process. Now, this becomes a little problematic for domain and generic because those tickets are more likely to rely on terms that are less frequent and possibly less unique to the class, since the actual words that are more frequent in the class get weighed less because of the TF-IDF process. And that leaves me at n-grams. I'll start by defining a few functions for generating all possible n-grams for my data. Those are here. And I'll store the n-grams and a string of the n-grams in new columns in the data frame. This column has a list of our n-grams separated by commas in the list here in normal Python fashion. And then this other column has the n-grams just separated by a space. And this is the format that we use to pass them to our graphic generating functions. Then I'll combine all the n-gram strings for all the text and for each class and generate some graphics with them. This is the same thing that I did earlier, but instead of using single words as our tokens, we're going to be using the n-grams as their tokens. So using the n-grams from all of our tickets, we can see a lot of familiar terms paired up with each other. Most notably is password reset. That's number 1 by a long shot. And then for the individual classes, the influence of our common terms like password, reset, and login are tied together with more class-specific terms like SAP, Chronos, and so on. For example, login still matters quite a bit in mid-range, but now it's tied in with AS400 login. So that's more meaningful than just login. And upon closer inspection here with generic and domain, we can see that they are fairly different. Domain has password reset, needs updating, users UPN. You'll see quite a few of these have UPN in them, and generic doesn't have that, at least not as much, but they do still have that main password reset. But the similarity is enough to account for that roughly 10% overlap that we saw. I'd like to take a moment to point out the fact that even with this confusion between domain and generic, this model is on par with human level performance. A human isn't going to be 100% accurate either, and they very well may be a whole lot worse than 90–95% accurate. So using NLP to categorize the bulk of the incoming tickets and then having a human look at only the tickets that get sent back as uncategorized will likely give you better results for a lower cost. And with that, that is the end of my demo, and I'll hand it back to you, Tom.
Hey, thanks, Mateus. Thanks for the demo of natural language processing. Let's turn our attention now as we head in the home stretch into deep learning and using neural networks. Now let's talk about what an artificial neural network is at a very base level, and you'll see the example here on the screen. What you're trying to do is replicate the human brain using a computer algorithm. Very specifically, what you see on the screen is a neuron. You see a human neuron on top, and then what would be an artificial neuron right below it. Typically, you use artificial neural networks, or what are also sometimes called synthetic neural networks, or just for short, you'll hear them called neural networks, to actually do regression or classification. And you'll see the diagram on the right, you have multiple layers. You have an input layer. The data comes into that layer. The input layer then outputs to one or more hidden layers. So in our diagram here, you see one hidden layer, but there are actually going to be multiple hidden layers. And ultimately, it feeds through those multiple layers to an output layer. You're replicating the human brain, an artificial neural network. The way to think about each of those layers, what you see, the circles that are blue and green there, and ultimately to the red, they are the nodes or neurons. And what they do is basically three things. Input comes in, they are a function. You'll see that there in the middle where it mentions the word bias. There's a function that has some thresholds that are used to then ultimately give you output on the other side. So that's the basics of what you're trying to do in an artificial neural network, replicate the human brain using multiple layers. So just examples of how artificial neural networks are used. You can see many of them listed here: part of speech tagging, semantic parsing, and question answering, right? More complicated natural language interaction. You can have multi-class text classification. That helps. And again, going to the ticket analysis, even that Mateus was showing us, you can take it to a next level using multi-class text classification. Translation, you've probably seen this with Google Translate. You can take it to hiring decisions, tumor identification, and we'll see here in a second how it's used in fraud detection. Probably the most common one that most of us are used to that you never see is the Google search engine. Behind the scenes, there's an artificial neural network. So with that, let me hand it off to Anthony to give us a demo of artificial neural networks and how it's specifically used in fraud detection.
Thanks, Tom. All right. I will keep my slides light. So the use case I have here is pretty simple. We want to use, 2 days of credit card data. And in that credit card data, we have something like 284,000 transactions. And of those, 284,000 transactions, less than 1% of them are actually fraud. So we have a data set that was labeled with fraud or not fraud. So it's a minority representation of fraud. And we'll talk about that as well. But the use case is credit card fraud detection. So if you're in the financial sector or you work anywhere with fintech, or even if you have a credit card, it's important to understand how these things are used to protect you and your customers. So it provides better customer service, better risk management, near human level performance, consistency, reduced cost, faster resolution times. And when you couple it with automation, it even further reduces costs. So you can leverage machine learning much like you could conditional logic and programming to say, if this happens, do that. When you get the output from the model, you can have another application take that data as input and perform a function. So I can show you code, and I will, but I just want to give you the basics of how we go about this, right? It looks like a lot when you look at a Jupyter notebook, but really we're starting with a use case and a data set. We then start to go down the path of model development. Model development incorporates things like loading the data, exploring the data, pre-processing the data, basically cleaning it up if it's got a lot of junk in there. And then if it's numerical data, we'll have to scale it. So in this case, we're dealing with financial, so we're dealing with numbers. And that data will need to be scaled. So when you think about scaling, consider, the number 1 as the number of times the event occurred, maybe, and then the value or the cost or the value of the transaction being 1,000. So if I tried to graph, 1 and 1,000, they're going to be way off scale. So we put them all down to values between -1 and +1, and somewhere in between from a decimal value. After we scale it, we then build and train the model. We evaluate that model, and we save the model. After we save the model, we may go down the path of building, and I won't be demonstrating this, we have in other webinars, but we would build an API or user interface. We would also add a human in the loop function to handle low probability predictions. And then once it's deployed and all the interfaces are built, aside from the model, we would then hand it off to ML Ops, which would effectively have it deployed. And during that ML Ops process, and this is a very abbreviated version of the methodology, we're going to deploy, monitor, and constantly improve. So with that being said, let's go to the demo. Okay, I'm not a robot, or at least I don't think I am. So what we have here is the Jupyter notebook. And if you go into the crash course folder, you'll see the neural network folder, and you'll see this TensorFlow credit card fraud neural network work in progress. It's not a work in progress anymore. So what I did with my data set, because this data set is relatively large, is I hosted it in my Google Drive, and then I mapped or mounted my Google Drive through this button here in the Jupyter notebook. First thing we do is load our libraries. I've already loaded them. We then mount our Google Drive. If you don't have the data on Google Drive and you uploaded it as temporary space, you can open the data frame this way. So the data frame is effectively just a programmatic way to read CSV data or a spreadsheet for this in this scenario. So we're going to read pandas, read the CSV, and that's the CSV file. You will not need these 2 or 3 to do that. You can remove them and start over. Once the data set is loaded, which we talked about in the graphic, we then start to explore the data set. And we notice some very interesting things right off the top. There are 31 columns. And what we have is time, and then all of these different scenarios, amounts, and a class. And the class is basically fraud, not fraud. The amount is the amount of money that it was there. And everything else has been obfuscated because naturally this is protected data. So time is available, amount is available, class is available, meaning fraud or not fraud. So we have 31 columns in this data set. And of those 31 columns, we're going to use 0 through 29, which is 30, as input to our model. We're going to use all 30 to determine, based on training, if it's fraud or not fraud. So the data, when you look at it, has all these interesting values. These are responses from the credit card processing company and how they track that information. But you can see the amount is relatively easy to understand, and the class is very easy to understand. It's basically a 0 or 1. So that's going to be a binary decision, a 0 or a 1, off or on. When we look at the counts of fraud versus not fraud, this is not fraud. There are too many, and fraud, there are only 492. If we plot that, you can see that this is a scaling issue. It is also a completely imbalanced data set. So the ones hardly show up and the blues are taking over. So this is not fraud. This is fraud. It's almost undetectable. If you want to look at it from percentage perspective, there's some code in there. You can see that it is less than 1%. If we wanted to build a visual to understand where that data exists across that entire set of parameters that they use to track, you can build a heat map. This is just an interesting way to look at the data, because looking at numbers like this can be painful. There are 3 different ways to build a heat map. I used Seaborn twice if you're a Python programmer, and Matplotlib, PyPlot. After we go through and do some exploratory data analysis and identify that our data is imbalanced, we're going to go through and create our independent and dependent variables, which is effectively our X and Y. When you're presenting input to a model, you need to give it at least 2 inputs. Some models require more, but what we're talking about here is the X and Y value. So for X, we're basically taking everything and dropping the class, meaning we don't want the class. And for Y, all we want is the class. And these are just commands that you use to do that. Then when we print them out, you'll see that X equates to everything except class, and Y equates to only the class. From there, we scale the data. Again, we want to make it, we want to offset things like 123 to 0.06, right? If you're looking at these on an XY coordinate, these are going to be off the scale, right? They're not going to show up the same. So we scale the data. And that data, once it's scaled, basically makes it anywhere from, -2 in this case to +2. So you can see the numbers all change. Every one of those values in that data frame here changed to some other representation here. And that's all tracked through inverse transform. This is a transform. So if we wanted to see the opposite, we could always pull back the original data. Much like Christian did, we're going to use SMOTE, synthetic minority oversampling. And we're doing this because we have 492 fraud samples in almost 300,000 records. So we have to fix that to train a model effectively. So I use the imbalanced learn library, and I use the SMOTE technique. So when we start out, we have this count, and after I oversample, I wind up with this count. So now I have effectively representation of both classes, fraud and not fraud, in equal terms. So now I can train the model. Now that I've manipulated the data to properly input to the model, I can now train split my data into a train and test. In this case, it'll be 20%. So I have X train, X test, and so on and so forth. Then we go and build the model. Since this is a neural network, when you looked at that image that Tom showed you where you had all these connected dots, this is the code that connects those dots. So each one of these is a layer. My first layer is the only one I have to specify the input. So I know that I have 30 variables. I'm going to use 128 units, and my activation is ReLU. So rectifier linear unit, you don't need to know that. There won't be a test later. But I have my first layer that's input. I'm basically saying I'm going to send this data through each one of these layers. And when I send them through each layer, I'm going to drop out 20% of the data before I send it to the next layer. And my last layer, the output layer, only really has one option, because it's either a 0 or a 1, which makes it binary. So I only need one output. I specify my metrics as I'm training for accuracy, precision, and recall. Then I'll go through and compile the model. I cannot do this live because it took about 45 minutes, and that's with a Google TPU, which is a fancy name for tensor processing unit, as opposed to a GPU or a CPU, which you may be familiar with. When I'm all done training, I'm going to print out my recall and my precision. And you can see that when the model started training, it was only 21% accurate. And then as it moves through each one of these epochs, epoch is a period of time, right? Think of this as 50 epochs, or we're sending this model to 50 semesters of school in a very short period of time. So it's going to learn a lot. It's going to start out with very little knowledge. And when it's all said and done, the model will train at an accuracy level of 88%. I know from running this model on my local workstation, then I can get this over 96, around 94.7% on accuracy and recall. So I stopped at 50. Once we're finished with that model, we then have this output, right? We talk about precision and recall. What it's really trying to do is identify, based on the retrieved elements, which are relevant and which are, true positives, false positives, true negatives, and false negatives. So basically, how confused is the model? And there's a link here if you want to look up what precision and recall is. If you're interested in learning about machine learning, especially neural networks, you're going to need to understand this concept, but it is not very difficult to understand. So you can see here, precision is how many retrieved items are relevant and how many relevant items are retrieved. And they're used together. This is just a visualization of the model. This is just plotting the model. So you can see, if you had to send this to management or explain it to somebody, this would give them the closest thing you can get to a non-technical description. And last but not least, we evaluate the model. And what this does is take that test set that we split from the training set and runs this whole, uses the model to evaluate how accurate it is on data that it was not trained on. So you can see here that our accuracy was almost 93%, recall, 3 nines, and I'm sorry, precision 3 nines and recall 1. So this is a pretty solid model, pretty accurate. And the way that we can make it better is by making the data set better, or by hyper tuning the parameters of the model. One thing I can tell you in machine learning, data science, you're going to spend more time tweaking the data set than you do tweaking the model. However, messing around with and I say messing around because it really is a trial and error in a lot of cases, messing around with the hyperparameters, meaning the number of inputs, the number of units, the number of layers, all of these things will affect the performance of the model. So with that being said, that is the end of my demo. And back to you, Tom.
Hey, thanks, Anthony. So let's just kind of summarize where we've been. We've heard a lot about AI, a lot about ML, a lot about natural language processing. I realize this has been one of those drinking from the fire hose experience. It's what's called a crash course. No doubt, a lot to consume, but let me remind you of a couple of things. One is the demos that you saw, the code and data is available online to actually download and use and try out yourself. You saw in the interface that we use Google Colab to do the demos. That is free. If you're not familiar with Jupyter Notebooks, which is what we're using in there, that's just a format that's used to do the actual coding. Another, just kind of think of a form of an IDE that you can use. We use Python, so you can actually go through and see how it's done in Python. You can also do it in R, but we use Python. You can get familiar with that there. Hopefully what we did today was give you a basic understanding of machine learning, natural language processing. We gave you a place to start, kind of a fighting chance. At a high level, we wanted to frame out for you what it is. So you have places that kind of hang the vocabulary and the idea of how it worked. And what we hope the demos did is show you not only what you can use it for, but how the sausage is actually made, what it looks like under the covers. If you have further interest, maybe this sparked some interest in other topics, you can let us know. You'll find our contact information on our website, which I'll show you briefly here in a second. You have any questions or specific use cases you'd like to discuss with us, please feel free to reach out to us. So let me just jump over and give you a little intro to CMG itself, very briefly. We're a small company, and what we focus on is building IT automation integration experts who are day one ready to deliver IT and automation integration services. One of our areas you'll see is machine learning and natural language processing. The core practices we cover are DevOps, DevSecOps. We have some other webinars we've done on that. Machine learning, natural language processing, cloud architecture, and integration. It's really our goal to be a go-to partner for IT automation engineering or IT automation integration services. The service offerings that you'll see over there, right, they range. We'll do everything from contract to hire, staff augmentation, managed services, custom solutions. If you have any interest in these, we just encourage you to reach out. You'll find and you'll see here links to our website, careermentorgroup.com. On the site, you can actually find there our offerings. We have a link to our blog. that's on the site as well. You can find and sign up for a monthly it's not monthly, but our newsletter that goes out. We send one out generally quarterly. If you have interest in connecting to us, you can follow us on LinkedIn. You'll find us there. And if you're in the Twitterverse, you can get a good tweet every now and then on Twitter as well. So with that, let me hand it off to Jen to wrap up everything.
Okay, cool. Thanks, Tom. For those of you in the Central Texas area, we would love to have you join CMG for our Automation Engineering User Group, which is kicking off on January 27th with our first stop being in Austin. I'll go ahead and put that link in the chat. You guys can check out the site and register to attend if you'd like. We will be having other locations listed within the next month or so.